Hi, we're going to start the focus on statistical thermodynamics. So this is focus 12. And let me just look at the camera. Okay, so focus 12. This is, I think, something that's a really interesting area of thermodynamics, and it's something that you probably haven't seen in any other class. So hopefully you find it interesting too. So we're going to talk about connecting two of the areas we've learned about. So we've learned about energy states in quantum mechanics, this discrete energy levels of atoms and molecules. And we've learned about thermodynamics in general, the idea of the first, second, and third law of thermodynamics, what kind of what direction change happens in. So what is a spontaneous change? And mostly in thermodynamics, we learned, which will be important here, is where is equilibrium? So what does it mean to say you're at equilibrium? So it's statistical thermodynamics because we're just going to use statistics to connect those two big areas. So we're going to look at, on average, what are molecules doing? And therefore, what does that tell us about the properties of a bulk system? So the first topic we're going to go through is something called the Boltzmann's distribution, which we read about a little bit in the start of this course when you think about the population of states, and you've probably used this in other classes too, but you've never actually seen where it came from, I don't think. Out of the Boltzmann's distribution comes something called the partition function. We'll learn a lot about that. It's almost like a wave function in quantum mechanics. It contains all the information about thermodynamics that you can obtain. And so we'll use that partition function to then take our Boltzmann's distribution and link that to things like what's the Gibbs free energy, what's the enthalpy of a system. So first thing we want to learn about is the Boltzmann's distribution. So it's something that you've seen before, and the total distribution is written right here, which says the number of molecules in some energy state I divided by the total number of molecules. So this is the fraction or the population of the I state. Is equal to this exponential function. So e to the minus the energy of that state divided by kT, Boltzmann's constant times temperature, divided by this thing called the partition function. And the partition function is similar to the numerator, but it's just a sum over all the states that the molecule or the system has. So sum over I, sum over every energy state. And so you can use that then to take a ratio. So you could take a ratio of how populated the I equals 2 state is to the I equals 1 state. And then the n would cancel when you took that ratio, and you'd end up with, it's simply a ratio of those exponential terms. And so it's really a function of how far apart the energies are. So if they're super far apart, then the second state won't be very populated because you'll have a negative big number. And the temperature is the only parameter in here that controls these relative populations. So the temperature is essentially defined by how it impacts the distribution of energy over the states. So it's another important thing. You end up realizing that, so Boltzmann's constant times Avogadro's number. So Boltzmann's constant is essentially a gas constant per molecule or per atom. So if you multiply by Avogadro's number, you get the gas constant. And so it's interesting that you essentially have the gas constant within this partition function, which tells you about the distribution of energy. So it really tells you that the gas constant is has a greater physical significance than just PV equals nRT. So it's going to pop up in weird places like this. So the gas constant in this equation, when you talk about molar energies, is just a sign that the gas constant is bigger than just something that deals with gases. So here, when you have the relative populations, if you're talking about individual energies of molecules, you're using K. But if you multiply top and bottom by Avogadro's number, then you have energy of a mole, and you have the gas constant instead of Boltzmann's distribution. So just think of Boltzmann's constant as if it's the gas constant per individual atom or molecule, and the gas constant is per mole of those. So the relative population of the upper state decreases exponentially with its energy above the lower state. So that's just what's clear here. If this gets bigger and bigger, you have a bigger negative, and this ratio gets smaller. So that population of an excited state decreases as it gets further away from the energy below it. So when we look at what that means about different types of energy, electronic states are super far apart. And so at room temperature, probably just the ground state's populated. And then vibrational states are closer together, but further apart than rotational. So it's also true that at room temperature, mostly all the molecules are in the ground state because that difference in energies is big. But rotational states are pretty populated. So you'll see that there are more populated rotational states because that energy difference isn't so big. So that exponent doesn't get so small. So an important thing I just mentioned is that the temperature is the single parameter that controls those relative populations. So there's no other parameter in here to describe the system except the temperature. And so when you look at what that means, the temperature, if temperature is 0, then you have e to the minus infinity, and you essentially have the relative population of the excited state is 0. So that means at T equals 0, you only have the ground state populated. As the temperature goes up, you get a greater number of molecules that can be in excited states because temperature gets bigger, and that makes that number smaller. E to the 1 over a bigger number makes that smaller, so you get closer to 1. And then that continues. And if you're at T equals infinity, then you have e to the minus 0, and this ratio would be 1. And so that means that all of the states are equally populated. So this is what happens to the population of states as the temperature changes. Yeah, so Boltzmann's distribution really shows you why at low temperatures, molecules are all in the ground state, so you're not going to have a lot of chemical change, a lot of bond breaking or anything because you're in the ground vibrational state. But as you go up, if you have highly excited vibrational states, you're going to see that you can start breaking bonds. So the Boltzmann distribution explains why molecules are stable, but then it also explains why molecules can undergo chemical reactions. So for this test, it says self-test 12A.1, determine the temperature at which the relative population of molecules in axial and equatorial conformations in a sample of methyl cyclohexane is 0.3 or 30%. So the fraction is 0.3, then that's the number of molecules in one state versus the other. I can put that in here. And then I can take the difference in those two energy states, which, yeah, they gave us up above. The equatorial form is lower in energy, with the axial form being 6 kilojoules per mole higher. So 6 kilojoules higher is the axial form. So the difference in the two energies is 6 times 10 to the third joules per mole. So that's the basically this right here, the difference in the energy of the axial minus equatorial, and then divided by R and T, we're solving for T. And when I do that math, I got T of 601 Kelvin. So that's what they got too. So when we look at this general form of the Boltzmann's distribution, I showed you this already, and I showed you this. So this is just saying this is the general form where the population of a state is its energy in an exponential function divided by a sum of all those same functions for all the energies. And if you happen to have degenerate states, so something like the p orbitals, and you wanted to know what's the population of any p orbital, you'd have to take into account the degeneracy. And so the degeneracy is the number of states with that same energy. And so the population of that whole level would be the population of any one state times 3, because you have 3 p orbitals. So you can write the partition function as a function of the degeneracy too. So it's like saying, if I add together 3 terms that all have the same energy, I could have just had one term and multiplied it by 3. So the next self-test is one that deals with that degeneracy concept. So the self-test says, what's the ratio of the population of the levels with J equals 1 and J equals 0 at the same temperature? So we have HCl in this problem, and it's at 25 degrees, gives us the rotational constant of 318 gigahertz. The energy of any state, we knew this from quantum mechanics, was Planck's constant times the rotational constant times the quantum number of the rotational state times the quantum number plus 1. The degeneracy is 2J plus 1. So if you're in the 0 state where there's no rotational energy, the degeneracy is 1, because J would be 0. You go up 1, and J equals 1, so it'd be 2 times 1 plus 1 would be 3. So the degeneracy continues to increase as you go up. There are more states with that same energy. So we are asking the question, let me make sure I remember, what's the ratio of population of the levels with J equals 1 to J equals 0? So J equals 1 has a degeneracy of 3, so this is 3. And when I take the ratio of 1 to 0, the n cancels, and I essentially just get this ratio of numerators. So 3 for the J equals 1 state, and then the energy of that state would be H rotational constant, and if this is a 1, it would be 1 times 1 plus 1, so it'd be 2. So you'd have this energy, and then you divide it by kT if we're talking about individual molecules' energy. For the state with J equals 0, then the energy is 0. So it's 1 for the degeneracy times e to the minus 0, which is 1. So you end up with just the numerator, because the whole denominator equals 1. And so you get 3 times 0.903. So if I put all these in the right units, knowing that a hertz is 1 over seconds, Planck's constant is joules times seconds. And if you put this also in joules, you'll end up with the right units. So I got the ratio is 2.71. Is that what they got? Yes. So when you take into account degeneracy, oftentimes for rotational states, the ground state isn't the most populated. So when we looked back here, for any other system, the ground state will be the most populated. But if you have degeneracy, then even though you're going up in energy, if there's more states at that level, it's going to be more probable. And so you'll get a partition function that looks different from that. Okay. So with that, and then as a convention, we're going to set the ground state energy to be 0. And then we're going to have everything measured relative to that. So that means if for a harmonic oscillator, the energies are 1/2 h nu, 3/2 h nu, 5/2 h nu, you're going to set the first one to 0 and then subtract 1/2 h nu from each of these so that you're just looking at how far is each state from the ground state. So 1/2 h nu is 0. So 3/2 h nu minus 1/2 h nu is just h nu, 2 h nu. You'll do that with whatever kind of energy it is. So in the next section or the next topic, when we look at how you actually use the partition function, that will be important. So where does the Boltzmann's distribution come from? And this is something that you'll derive in bloody detail if you take 366. So the important thing to think about is the Boltzmann distribution is the most probable outcome of the blind chance occupancy of energy levels, subject to the requirement that the total energy has a particular value. So when you look at this picture, it's showing you how you could distribute energy when the energies are all separate, rated by the same amount. So this would be something like harmonic oscillator. So if you have the same total energy, all of these guys would be 0 in the ground state. All of these guys would be h nu, 2 h nu, 3 h nu. So if you add together the total energy for each of these, if each level adds an h nu, you'll see the energy is the same and the number of molecules are the same, but it's this distribution that will be the Boltzmann's distribution because there are more ways to do this. So if we remember back to our definition of entropy, the most probable state is the one with the highest entropy. And this says that there are 181,180 ways for this energy to be distributed this way. So if you have this many molecules, which one's in this state, which one's in this state, which one's in the ground state? There are close to 200,000 ways to do it. For this one, there are 858, only 78, and this one there are 12,870. So this would be the one with the greatest W, and therefore the greatest entropy, and that's what the Boltzmann's distribution is. It's where does equilibrium lie? It lies at the maximum entropy. And so when you think about where all of this comes from, it comes from starting out with Boltzmann's definition of entropy. Entropy equals Boltzmann's constant times natural log of the weight. Weight is can be determined this way as the number of total molecules factorial and then the number in each state factorial. And depending on how many states you have, that can get pretty crazy. And so in order to derive the Boltzmann's distribution, we want to take the derivative of entropy with respect to the population of each state, and we want to set that equal to 0 because we want that to be a maximum. We want entropy to be a maximum, and we know when you take the derivative, you get maximum and minimum. And so that will be equal to k times the derivative of ln of w over ni, because this is just a constant. So if you're taking the derivative of this with respect to ni, you'd have to take a sum over all of these. And you set the constraints that all the molecules, so if you have 2 in the first excited state, 2 in the second excited state, you add those all together, it has to equal the total number of molecules you have. And if you add together the energy of each state times the population of that state, it has to equal the total energy. So if you take 366, you'll see how you solve this equation, finding the maximum entropy, setting those constraints, and that's how you end up with Boltzmann's distribution. And so that is that. And the important thing is we're talking about equilibrium. So Boltzmann's distribution is only valid if you have a system at equilibrium. But it turns out if you have a significant number of molecules, any of these other states will be so less probable that the Boltzmann's distribution is really the only population of states that you have to worry about. So equilibrium and statistical thermodynamics deals with large systems. You're not talking about 2 or 3 molecules, you're talking about large systems of molecules. So we will come back and we will talk about Q a little bit more, and then we'll take that to how can you actually derive an equilibrium constant in terms of Boltzmann's distribution.